So what is the derivative? Remember, it's the instantaneous rate of change at any given point on the function. It's the slope of the tangent line. And because it's the slope of the tangent line, we could use the derivative to actually write an equation for the tangent line. So we have a function, and now let's write an actual equation for that line that touches the function at one given point. So we use the derivative to find the slope, and then we use the point on the function where it touches the function to get the point that we need, right? Because to write any equation for any line, I need two things. I need a point, and I need a slope. And then I'm just going to use point slope form to do that. So if you think about it, here's my function here, and here's its tangent line. That's a really straight line. And it touches at this one little point right here, right? So I'm going to use the slope that I found using the derivative. So I'm going to use the derivative to give me that slope, and then I'm going to use this point. So it's the point on the function where the tangent line touches to write this equation. So let's see how to actually do that. First, we're going to find the equation of the line tangent to that graph at the point 1, 6. So first thing we need to do is find the derivative. So we find f prime of x equals, now because we have derivative rules, this is going to be really easy, isn't it? Okay, so we bring the 5 down, and I get 20x to the 4th minus 6x plus 0. Okay, and then I need to find the slope. That's a function, right? That tells me at any given point what the slope is. But I need to know the slope at this specific point. So I need to find the f prime at 1. So what is the slope when x equals 1? Well, it would be 20 minus 6, which is 14. So the slope of the tangent line, remember m represents slope, and I put a little tan there to tell me the slope of the tangent line is 14. That's my slope. Now, to write the equation of the tangent line, I already have a slope, and now I need a point. Well, it's at the point 1, 6, because if I plug 1 into this function, I get out 6. So when x equals 1, y equals 6, even though they told us that. Okay? So I can write the equation of this point, or this line, y minus 6 equals 14x minus 1. And then we're done. We just leave it in point slope. Don't ever, ever simplify it unless you have to. Because again, you're going to simplify wrong. I mean, I have faith in you, but you might simplify wrong. So just leave it unsimplified. Okay. The equation of the normal line. So if we go up here and we look about what the normal line is. Now the normal line is a line that is perpendicular to the tangent line. Okay. So if we want to find the equation for the normal line, since it's perpendicular to the tangent line, it just has an opposite reciprocal slope. So if the tangent line has a slope of 14, then the normal line is going to have a slope of negative 1 over 14. So the slope of the normal line equals negative 1 over 14. And so the actual equation for the normal line would be y minus 6 equals negative 1/14 x minus 1. Because it still goes through that same exact point, it just has a different slope. Let's look at non-differentiability now. So sometimes the function is not differentiable, and at any moment it'll catch up with me, but we'll talk about this. So think about it. First of all, if the function does not exist, can we take the derivative of it? No. So we can't take the derivative anywhere that the function doesn't exist. And where does a function not exist? At domain restrictions. So anytime we have a domain restriction or a discontinuity, we cannot take the derivative. Now you notice why we talk so much about discontinuities, right? Because they help us with limits and derivatives. So if I have a discontinuity like a hole, there is no derivative. If I have a discontinuity like a jump, there is no derivative at that point. If I have a vertical asymptote, there is no derivative. So these three things, this is where the function does not exist, therefore there is not a derivative. That's these discontinuities. Now, there's a few other places where we cannot differentiate, even if it's continuous. So we can't take the derivative if we have a sharp turn, like in the absolute value function, or where we have a vertical tangent line, like in the cube root function or like the fifth root function that's really, really flat. The tangent line goes vertical, and a slope of a vertical line is undefined, therefore there is no derivative, right? Because the derivative would be undefined. So these two functions are continuous but not differentiable at these points. These functions are not differentiable because they are not continuous. So a function has to be continuous at that point, and it has to have no sharp turns and vertical tangents. So some of them you're going to be able to see right away. A lot of them you're not going to be able to, so I'll show you how to find them. Yes, okay, I said that. I wanted to make sure that I had said that. Okay, so find the x values where the function is not differentiable. Okay, so this first one, we just have to know what the function looks like because we know our parent functions. And so we know that there's a sharp turn when x equals 0. Because at x equals 0, there's that little v. So we can say at x equals 0 because of the sharp turn. Okay. The next one, we have to find out if it's not differentiable. So what does it have to be differentiable? It has to be continuous, and it can't have any sharp turns or vertical tangents. So let's see, is this function continuous? That's the first question. Okay, if the function is continuous, I would put 0 in for x squared and 0 in for x, and when I put them in, I do get them out because, again, let's just picture this one if you have to. So we have a parabola and then a line. Okay, so first of all, it is continuous, so that's a good sign. We know it's continuous. But now what we have to do is we have to check to see if there's a sharp turn there. And the only way to really check that algebraically is to see if the derivative here is equal to the derivative here. So if the derivative of this function at 0 is equal to the derivative of this function at 0, then we're going to have a differentiable function because the derivative doesn't like go from, suddenly like this all the way to like, right? Because that wouldn't be differentiable at that like sharp turn. Yeah, just a sharp turn. I was trying to think of a cooler way to say it, but really it's just a sharp turn. Okay, so we look for the derivative at this point. So f prime of x equals 2x when x is less than or equal to 0, and just 1 when x is greater than 0, because I just differentiated each of those. So now I check to see if the derivative is equal at 0. So the derivative of f of 2x at 0 would be 2 times 0, which is 0. And the derivative of this second part of the function, so the derivative here, well, when x equals 0, this equals 1, because it always equals 1. So the derivative here is 0, and the derivative here is 1. Do you see how the derivative of this function is not equal to the derivative of this function at that point? Therefore, this is not differentiable at 0 because there's a sharp turn. We know there's a sharp turn because the derivatives are not equal. I know I'm saying it like 100 times over and over, but you'd be surprised at how hard it is to just remember that. The derivatives have to be equal in the piecewise function for it to be differentiable at that point. So where does this have where is this non-differentiable? At x equals, oh, I always grab the highlighter instead. At x equals 0 because of a sharp turn. All right. Let's look at this other piecewise function. So the first thing we need to check is if it's not continuous, it is not differentiable, period. So we check for continuity, and then we check to see if the derivatives are equal. So is it continuous? Well, to check for continuity, I see what is the function, what is this function equal to at 0, and what is this function equal to at 0. So this first function at 0 is equal to 0. At 0, this function is equal to 1. So these functions are not even continuous. One of them is a parabola, that goes to the origin, and the other is a parabola that's shifted up 1. So these are not continuous, so this is not differentiable at x equals 0 because it is not continuous. And we can put because there's a jump. What about this one? Well, first we check for discontinuities, because if it's discontinuous, that's where it's definitely not differentiable, where it's discontinuous, and then if there's any sharp turns, it's also not differentiable. So we look, there is a hole at x equals 0, and there's a vertical asymptote at x equals 1. So it's not differentiable at either of those places because of those. And then is there any other sharp turns? No, because this function is just a rational function. This is just, once this hole, is gone, this behaves like just the plain old rational function. So everything else is fine. You're going to see those sharp turns in piecewise functions, in absolute values, and yeah, that's about it. Possibly in like the greatest integer function, you're going to see jumps. But most functions are continuous otherwise. Okay. And then let's look at this one. What is the derivative of this function? So the first thing we want to check is we know the cube root function. It looks like, it looks like this. And so we know there's a vertical tangent there, but how do we know that? How do we know that with algebra? So we would say the derivative of f is 1/3 x to the negative 2/3. Okay. So the derivative, the slope of the tangent line, is this function right here. Let's rewrite that as 1/3 x to the 2/3. Then we can even rewrite that a little bit more if we want. I could write that as 1/3 times the cube root of x squared. Okay, so now this is the derivative right here, and I have to figure out, where is this not differentiable? Well, it's not differentiable anywhere where the derivative has a discontinuity, right? If the derivative is not continuous, then it obviously isn't differentiable. So what number, if I put it in here, would make the derivative do something illegal? Well, if I put 0 in the denominator, then this whole thing would become 1 divided by 0, which is not possible. Therefore, the derivative does not exist at 0, right? It's discontinuous when x equals 0. When x equals 0, the derivative is not continuous. The function is continuous at x equals 0. Therefore, that means this is a vertical tangent. It's where the tangent line would have an undefined slope. So again, we can picture it, but with algebra we can just find where the derivative would do something illegal, and that's where we have a non-differentiable area.